This is third part of the second lecture of week 9, where we discussed linearity of the inverse Laplace transform. Let me formulate the theorem. Assume that Laplace transforms of inverse Laplace transforms of the function f, let's say f1 and f2, exist and continuous on the semi-interval, and also we assume that c is some constant. Then the inverse Laplace transform of a sum of these two functions also exists, and this is equal to inverse Laplace transform of the first function plus inverse Laplace transform of the second function, and the inverse Laplace transform of constant times f also exists, and this is equal to constant times inverse Laplace transform of the function f. This theorem will help us to find inverse Laplace transform, and the proof of this theorem I'm going to omit. It's given in problem 37 so proof is given in problem 37 for paragraph 7.4. Let me just show you an example. So, example, we need to find inverse Laplace transform of these three fractions. So, what we do, using the theorem for linearity of this inverse Laplace transform, we can write it as 5 times L inverse of 1 over s minus 6 minus 6 times L inverse s over s squared plus 9 plus 3 L inverse of, and also let's take out 2 from denominator, 1 over s squared plus 4s plus 5. And let's find separately each inverse Laplace transform. So L inverse of 1 over s minus 6 at a point t. This is, again we use the table, and we see that the formula, which is similar to this, 1 over s minus a. This is inverse Laplace transform of this is Laplace transform of e to the at. So this is e to the a is 6 in our case, e to the 6t. Inverse Laplace transform of s over s squared plus 9 at a point t. Again, we look in the table, it's very similar to this expression, and this is Laplace transform for cosine bt. So this is cosine, where b is square root of 9, which is 3. And inverse Laplace transform of 1 over s squared plus 4s plus 5. So here we have to complete square of this of the denominator. This is L inverse 1 over s plus 2 square, and here we have just 1 left, so 1 square. And this is similar to e to this thing here. So this is Laplace transform of e to the power at. A in our case, here we have minus a and here plus 2, so a is minus 2 sine, and b is just 1 in our case, so this is just sine t. So the answer is the Laplace transform. Let me put star here. The star equals, here we have 5 times the first inverse transform is e to the 6t, minus 6 times the second inverse transform is cosine 3t, plus 3 over 2 the third Laplace, inverse Laplace transform e to the minus 2t sine t. So this is the answer for this example.